So what we did yesterday here is we came up with the idea that we can take a force and model it as a vector. The length of the vector is the magnitude of the force becomes the length of the vector, and then we can take forces and add them as vectors, which is done in a graphical way, and we can add forces together. That's what we went through last time. All right, and we actually did it graphically because that's really what you're doing when you add up forces. You're going through a graphical addition of vectors to add them up. So do we have any questions on that stuff? Doing all right with that? Okay. All right. Now, there actually, back in the day, there used to be people who did a lot of what I call engineering mechanics problems that way. There are all these fancy graphical methods for doing them, and they taught them, especially to people in drafting programs, to do it that way. However, that's obviously not the way that things are normally worked out. We use trigonometry, and we work with vectors in that fashion. So let's have a look at page 140 here. And let's kind of see how we would do that same process that we did, but let's do it this time by using trigonometry to work through the vectors. All right. So a 2D vector, and we're going to stay in 2D to begin here, has components along the x and y axes. So what I've got here on page 140 of your notes is I've got a vector. Okay. And there it is, so it's going off like that. And what I can do is project that down to the x and y axes. So I can take that vector FA and I can break it up into FAX and FAY, okay? Two pieces. Now, the x and y directions can be signified. You know, we kind of get into the notational part of this stuff. I can signify that by using what are called unit vectors. So instead of saying in the x direction, I can use an I unit vector, and instead of saying in the y direction, I can use what I call a j unit vector. Unit vectors have a magnitude of 1 and point in a given direction. As I view them, they kind of serve as direction pointers. They're saying in this direction or in that direction. I says in the x direction, j says in the y direction. So what I can do, and this is just a notational thing, but we'll use this a bit. You can take FAX, let's say, and break it into two pieces. Okay, FAX, not bolded, not written as a vector, but just a magnitude, and then I for the direction. Okay, so I can take FAX and turn it into FAXI. And what I've got then on the left is a magnitude. On the right, I've got the direction. Just a notational thing that we use sometimes. Okay. Now, when I start adding these vectors up, you know, I have to be very conscientious of the direction of them. It matters quite a lot when I add them, all right? So I want to be aware of that. So if I'm going to add two vectors, I have to be careful because here's an example of what I'm talking about. Let's say I've got these two simple vectors. And let's say this is 4j, and this is 3i, and I'm going to add those two together, and I'm going to get the resultant of the two. Now, what happens when I add 4 and 3? What do I get for the magnitude of the resultant? 5, right? So you can't add x's and y's together arithmetically. You can't add the magnitudes together. It doesn't make any sense because they're not pointing in the same direction. You all with me there? So in order to add two vectors together arithmetically, they got to be pointing in the same direction. Okay? I can't take 3i and 4j and add them together and get 7. It just doesn't work that way. All right? So what I want to do here, if I want to start adding vectors, is I have to have a step before I add the magnitudes. I've got to break them up into x and y components. See, I can add the x's arithmetically, and that makes sense. I can add the y's together arithmetically, and that makes sense. Then I can come up with a total x and a total y. That's how I add vectors together. So when I'm doing vectors, there's a step that precedes the arithmetic, and that step is to do some trigonometry and get the components. Okay. So what I do here is for these two vectors, f, a, and b, I would use trigonometry, break them up into x and y components. So there's fax, and there's fbx, and there's fay and fby. I can add the two red ones, the x's, together and get the resultant in the x direction. I can add the two j ones, the y's, together and get the resultant in the y direction. Then I've got a total vector. Okay, I can do that. But I have to, before I can use arithmetic to add the numbers, I've got to be sure that I've got them broken up into directions so I can add the like directions together. That's the deal, okay? So if I end up with that, what's the general formula for the magnitude of FR? What do I do to get FR? What do I do with this? Yeah, I've got to go Theorem of Pythagoras, right? Okay, because I've got them in x and y direction now. See, I've got my total x doing that, and I've got my total y doing that. If I want to know how long that resultant is, I've got to use Theorem of Pythagoras is what I got to do, okay? So I'll go ahead and do that. I'll go sum of fx squared plus sum of fy squared and take the square root. That's how I find the magnitude of the vector. And I can also use some trigonometry here. Remember that a tangent is what? Opposite over adjacent. Okay? Opposite in this case is sum of fy. Adjacent is sum of fx if I'm looking at that angle theta. So if I take the inverse tangent, arctan, or sometimes called tan to the minus 1 of y over x, I can find that angle. Okay? So when I'm adding two vectors, doing it in this fashion, what I do is I use some trigonometry. I break them up into x and y components. I add the x's and the y's together. I take the square root of x squared plus y squared to get the magnitude, and I take the inverse tangent of y over x to get the angle. So that's how I add vectors in two space. Okay, and it's all just based on directionality, you know. I can't add an x and a y together arithmetically. It just doesn't mean anything. Okay? Yeah, y'all good with that? Now I got a little note down here. Are we good with all that? So we good? Questions on that? Now I've got a note down there. Be careful on these inverse tangents because for every inverse tangent there are two possible angles. And they're 180 degrees apart. Okay, a tangent is really a slope, is really what it is. It's y over x when you're kind of using the standard angles. If I've got these two lines, this would be positive 3 and positive 4. I'm going to run out of room here, but that's negative 3 and negative 4 over there. If I want the tangents of these, or inverse tangents of those two angles, what am I going to do? On the first one, I'd go arctan 4 over 3. And on the other one, I'd go arctan minus 4 over minus 3, right? And your calculator is going to run those numbers. It's going to do the fraction. It's going to take 4 over 3 and get 1.33333. It's going to take negative 4 over negative 3, and it's going to get the same number, 1.33333. Okay? And a definition of a calculator or a computer is a fast idiot, right? It does stuff, but it can't really think about it and analyze it. You've got to supply the intelligence. Okay, so it doesn't know the difference between those two things. So it's going to kick out by default the angles in the quadrants 1 and 4. If actually, see, this is quadrant 1 up here, right? If the answer is actually in quadrant 3, it won't know it. You're going to have to recognize that. Okay, so you got to watch this a little bit. You have to be the one who's deciding which quadrant it's in by looking at it. Okay, you all right with that? Okay. So why don't we do that same problem we did last time, but let's do it in a more normal kind of, modern way. And let's use a calculator, which I don't know, maybe that isn't the modern way anymore, I don't know, but let's use calculators and do it that way and use some trig, okay? So this is on, I think it's page 150, if I'm not mistaken. And I'm hoping everybody has that note packet by now. I mean, I think the lines at the bookstore are thinned out, and you really do need to have it and bring it with you, okay? It's important. All right, so let's have a look at this thing. Now, what we're going to do is we are going to take those vectors that we're given, and we're going to break them up into components. That's the first step. Now notice what I've done here. I've got a thing set up like a table, okay? I'm not going to run through a bunch of little kind of formulas with I's and J's and all that, okay? I'm gonna approach this like an engineer. I got a table. I'm going to fill in the columns, and then I'm going to add up the columns. See, when I'm doing calculations and I'm an engineer, I want to act like a spreadsheet as much as I can. I want to get everything nice and systematic and laid out nice and clean so I can just look at it and do it in a certain way. And I want to kind of emphasize that because part of what I'm teaching you is statics for sure. But the other thing you got to start learning is how do engineers do things and why. You know, we do things in a very systematic, laid out, clean way because it reduces the errors and other people can follow it. And it's the real hallmark of an engineer to do stuff like that, okay? That's why I'm doing it this way, okay? And I want you to start to mimic this because it helps over the long haul, okay? So what am I going to do? I'm going to take that 100 Newton force, and I've got a 53.13 degree angle, and I'm going to use that to get the x and y components, okay? So I've got a column for the force magnitude, that's 100. Now I've got a next column for the angle. Now I can do this one of two ways. I can call that angle 53.13, and if I do that, I've got to recognize I have to put the signs in by looking at it. The other approach I can use is always use the angle from the positive x-axis. Then I don't have to worry about the signs, okay? Now I prefer method number one. I just like to look at something and say, okay, that force, this particular one, is going to the left, isn't it? As I start right here, I'm going that way. That means that's a negative x. So I will put that negative sign in there. See that negative sign right there? Now, if you don't want to do that, you could always use the positive angle from the positive x-axis. The signs will just come out in the wash if you want to do it that way, okay? So I just want to point out that you can use either method. Okay, so what's going on here is I am using a little bit of trigonometry here, right? And if I'm using the angle from the horizontal, which I'm not always doing, but if I am, and I call this, do they have a letter for that? H for hypotenuse or something? I don't know what they use in math, I don't know. But this will be cosine theta h because that's adjacent, and this will be sine theta h, right? So if I got the angle with the horizontal, which isn't a given, but I do on this one, I'll use cosine for the x component, sine for the y, okay? And I just do a bit of right angle trigonometry there, okay? So I'm going to go cosine 53.13 times the 100 Newton magnitude. I got a negative out in front because I can tell that force component will go to the left, that x component. And then I've got sine 53.13 times 100, and that's a positive because that force component goes up. All right. So I get negative 60 and 80. All right. Now, if I just use that angle from the positive x-axis and a positive angle, which means counterclockwise, I can just go cosine 126.87 times 100 and sine 126.87 times 100. I don't got to worry about the sign then. Okay. You can do it either way. Just, be consistent in how you do it. So we okay with that? Negative 60 and 80 for the x and the y. We got any questions on that bit? Okay. All right. Now that next one there is to the left, it's 30. There's no markings on it, so it looks horizontal. If there's no markings on it, you can assume it is. So that's going in the negative x direction, so we don't have to do any undue amount of analysis on that one. It's just minus 30, okay? That's all it is. There's no y component. It's horizontal. Right. All right with that? Okay. How about doing that last one then? They've got the 134.16, 63.43. Get that broken down in the same fashion. Just take a minute and do that. Yeah, bring your packet, bring a calculator so you can knock through this stuff. You got questions? Yeah, because we're getting components of a total force. All right, making units on that. Watch your signs, just look at it, see which way it's going. Okay. Going down into the left. So, you know, X is positive right, negative left, Y is positive up, negative down. And then what you do, you just add the columns up and get the total. That's how you get the result. So the next step is just to add up the column. So work that down to negative 60 and negative 120. Does that sound about right? All right with that? Okay, so those are both negative because that vector goes down and to the left. Left is negative, down is negative. Okay, so they're both components are negative. We're doing all right? Any questions on that? Okay. All right. This is 4-credit class, right? So you're paying me $400 to be here, right? Make me earn my money, okay? You got questions, ask. Seriously. Okay? I'm totally serious about that. Okay, that's my job. And if you got one, someone else got it too. I guarantee that. I've been doing this long enough to know that. Okay. So we all right? Ask me a favor too. Just figure stuff out. Okay. So we good with that? All right. So then we just add them up, see? Just add up the columns, you get the total. So that's how you do that, all right? You could take negative 60, negative 30, and negative 60, you get 150 for sum of fx. 80, 0, and negative 120 gets you negative 40 for sum of fy. Okay. So that's the resultant vector, as we call it. When you take those three forces, add them up, the net effect, the resultant is that. So the word resultant vector comes from the word result, right? It's the result of adding those together. All right. Okay, now to get that, that's usable information right there. I've got an I and a j, which we use to specify x and y. All right. And then, okay. And again, I just want to call out attention to how the calculations are done there. Nice even columns, just add up the columns. Okay. I've surveyed before, in my working career. I've had somebody jump off their grader and come inform me that they thought one of my grade stakes was wrong, and they were polite about it, and I was polite, and we discussed it, and turned out it was good. But all the same, I had a company I worked with. They got a little deal with a bridge contractor because one of the footings apparently was set a foot too high. And they had a little, shall we say in quotes, discussion about how that happened. And that could be a very expensive little error, okay, extremely expensive, okay? And now we all screw up, don't get me wrong, but get good habits, start to develop them now when you're in school, where those little mistakes are not that big of an issue. So when you get out of school, you've got good, clean habits where you minimize that, okay? That's what we want to do. I mean, part of this is getting the grade and all that, and part of it's learning statics, but the other part is learning to be an engineer and the habits that'll help you succeed at that, okay? All right? Okay, we good? So now if we want to find the total force, we take the square root of sum of the squares, we get 155. And then if we want to find the angle, we do the inverse tangent of y over x. We get 14.9 degrees. Okay. And now we want to know which way does that angle point? Where is it going? Okay. And this is another little deal. This is a very visual subject, what we do. When I'm a civil engineer, I lay out pipes and stuff. I got to see that in my mind, or if I can't do that, I've got some problems. So I want you to start to develop that visualization kind of thing here, okay? Where's that going? I mean, what's it reference to? Which way does it point for that force? Yeah. Okay. And look at the tip-offs or the signs on the components, on the x and y component. All right. That goes down left is what it does, because both components are negative. See, positive 14.9 is going to come out of your calculator, but that isn't the right one. See, that's 180 degrees off of what it really is, and you have to make that adjustment just by looking. And the tip off, the key to that are these signs right here. See, that means it's going to the left, and the other one means it's going down, okay? So left and down, what that is that, see? It's going down to the left, quadrant 3. It's not a positive 14.9 degrees. It's actually 194.9 degrees is what it really is. Okay? Now, when I do answers on these things, and if I need to show a direction, I just show a sketch. I don't put just an angle. I just put my preference for a direction. If I ask you for it, is that. That tells me it's going that way. I don't just like you to write down 194.9 degrees. I prefer an arrow. It's doing that. Okay. We good with that? Doing all right? Now, if you look at that graphical one we did, that graphical one was pretty good. It was pretty close. I think we got 15 I think we even got it down to 155, and the angle I think I had was 195, I think, wasn't it, or 15 degrees? You know, a little bit different, but not, you know, pretty darn close. So pretty good. Okay. We good? So what just happened there was we did this. We took each one of those vectors and broke them up into x and y components. And then we added up the x's, we added up the y's, and got to these thicker lines down here. That's the process we just went through. Okay, we did it using trigonometry. Okay. All right. Okay. So that's how we do this stuff in 2D. Okay? That's the approach. Use trig and break them up and do that sort of thing. All right? All right, now the next step, of course, is going to be 3D. So let's have a look at that. All right? So let's have a look at some three-dimensional kind of stuff.